Scroll this up here. All right, very good. It is 40%. So, any questions on this? Going once? Twice? Okay. So, here's where we are headed next. This is the thing that when I was sitting in your seat how many years ago got me interested in chemistry. And at the time I was a music major and math major, and I got to this part in chemistry, and this is what changed me to decide to become a chemistry major. And that is chemical reactions and chemical equations. And so this here is chapter 7. And I'm going to start with some stuff that we've already seen, but we're going to look at it in a new context here today. And anybody remember, these are the same balloons as we saw in here on day 1. Anybody remember what we have in these balloons? Helium and hydrogen. And one of them here has a mixture of hydrogen and oxygen. And of course, I just can't bring these things out here without taking a chance here to inhale some gases, because that's what we do. We sit around as chemists, we have these parties, we bring these balloons.
Imagine a whole lot like the dentists do. They probably take their nitrous oxide out though, and they inhale that, and they're probably a lot more giggly. I've been told. Yeah. But when I inhale this stuff, that my lips kind of start blue after. I get a little lightheaded, and I'm not getting enough oxygen to the head. Are they turning blue? Yeah. Okay, and that's of course due to lack of oxygen to the head, and I start kind of getting a little crazier when I do that. And so, but what we're going to do here today is we are going to start off by kind of review, because of course review is fun, especially when it involves fire. And we got to turn down the lights for this. And we are going to go ahead and start with this first balloon. And I always have to remember, what are my colors now? So I come to this one. If you get startled easily, you want to cover your ears. All right, there we go. That one, of course, was helium. And now as we're going to learn, we look at the periodic table. And I'm going to stick in a periodic table here. And I'm sure you have yours out. Where do we find helium in the periodic table? Far right, over here. And of course, the elements in group 18, what do we call these?
Noble gases.
Noble gases. And in general, the noble gases we say are stable. They are non-reactive. We say they're stable, that means they don't react very easily. Sometimes we call them the inert gases. And if we use the word inert, what that means to chemists is that they are non-reactive. Now, if this is what you learned, as I probably told you when you went through this on day 1, you've been lied to a little bit. And the way you've been lied to is that it turns out that some of the noble gases do react with other things. For example, if we look at krypton, krypton reacts with fluorine. And if we look at xenon and radon, these two not only react with fluorine, but they also react with oxygen. So there are such compounds. I believe there's krypton krypton difluoride and krypton tetrafluoride. Xenon has several compounds of fluorine and oxygen, as does radon. But outside of those, the noble gases have not been found to react with any other elements. Now, hydrogen, which is the one we're going to look at next, appears over here on the left-hand side of the periodic table. And as we remember from day 1, it's a lot more reactive. If you get started easily, you might want to cover your ears. Well, that was fun. We'll try this. All right. So that's a lot more reactive, and as we are going to begin to find out, these elements here called what are these called here?
Alkaline.
Alkali metals. Of course, hydrogen's not an alkali metal, but we're going to find out these elements here of group 1 that include the alkali metals and hydrogen. Remember, hydrogen is the only element on the left-hand side of the periodic table
That is a non.
that is a non-metal, but even though it's a non-metal, it still has some very reactive characteristics like the rest of these elements here. Now, it does turn out that if we get hydrogen cold enough, if we get it down near absolute zero, turns out that hydrogen does in fact have a lot of metallic-like properties. If we can get it down and make metallic hydrogen, it does, not metallic, but solid hydrogen, it does have some metallic properties just like the other elements of that group. Now the last one here, you may recall, in day 1, is one that we need to protect ourselves a little bit. I'm going to be putting on some ear protection here. And in order for me to do this, you will need some ear protection as well. So you use your fingers in your ears. Need to make sure I get the flame first. And I won't do this unless your ears are covered. So cover them up. And of course that phone just likes to ring off the hook. I don't know. It used to call, whenever it came off the hook, it would automatically call the switchboard. And of course I'd hear all these students laughing and everything, and what's going on down there? And of course that one, in addition to hydrogen, contained oxygen. And so that's where we're going to start this off here with today, and we want to look at exactly what happens. So we're going to write down a word description of what happens. And in fact, it's the same thing that happened in the yellow balloon. The only reason why the yellow balloon didn't react the same way as the one over here and the blue one at the end is that this one here did not also contain oxygen in there. It still reacted with the oxygen, but the first thing that had to happen is the balloon had to burst, and once it burst, then it was able to react with the oxygen in the air. This one I have over here, also, oh my God, I have something hanging here. All right. The last one here already had oxygen contained in the balloon. So we're going to write out a word description here, and that word description will look like this. We say that hydrogen gas reacts with oxygen gas to produce. And any idea what we made when we reacted these two together?
Water vapor.
Water vapor, exactly. We produced water in the gaseous phase. And another name for water in the gaseous phase is what?
Clouds.
If we heat water up, what does it turn into?
Steam.
Steam, exactly. So we could say instead of water in the gaseous phase, we could say to produce steam. It would be the same thing. So now what we'd like to do is we'd like to write out a chemical equation that shows what happens in this reaction. First of all, what is the formula for hydrogen gas? H2. And why is it H2 and not simply H?
Because that's not how it's found naturally.
Yeah, hydrogen is one of those elements that we call a diatomic element. Diatomic element. And in case you've forgotten your diatomic elements, let's review those really quick. Your diatomic elements are hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine. And we learned it by the mnemonic Honkelgriff. Okay, and so this is hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine. And so all of these, when we see these as pure elements, we write them in their diatomic form. And so for this particular one here, we start with hydrogen gas. Its formula is H2. Then we reacted this with oxygen gas. So in a chemical equation, if we want to show reacts with, we put a plus sign in there to show that we're combining it with it. And then the formula for oxygen gas would be O2. And of course, this then is a gas as well. And then this produced water. Formula for water is H2O. And in parentheses, we put a label of G for a gas. So now, as far as what we write in these chemical equations, we do use what are called phase labels. And phase labels indicate to us what the phase is. And by phase, we mean such thing as G, which stands for gas. What else would we have? S for solid.
AQ for water.
AQ for neither aqueous. That's right. And as chemists, we usually pronounce it as aqueous. And then the other one we're missing is L, which stands for liquid.
What does aqueous mean?
What does aqueous mean? Dissolved in water. Means it's dissolved in water. And so if it's a liquid, that doesn't mean it's dissolved in anything. That means it's a pure substance. So these are the phase labels that we use. And very often we want to indicate those phases because sometimes the phase dictates to us whether or not a particular chemical reaction will occur or not. Now if we want to show this particular chemical reaction, I'm going to bring out the molecular model kits and show what happens in this reaction. We'll start with a molecule of hydrogen and a molecule of oxygen. And we'll put this up on the dot cam here. The white spheres here represent hydrogen, and the red ones represent oxygen. And so we need to kind of wait for the camera to get in focus here. Come on. I don't know why it takes this camera so long. There we go. So this here represents a molecule of hydrogen. This one here is a molecule of oxygen. So now in a chemical reaction, what happens is that collisions occur between molecules. They'll collide, and eventually, in this case, we had to heat it up. We put a flame up there, and that causes some bonds to break. And when those bonds break, then we begin to have bonds that will start to reform. And so I'm taking the pieces apart here, and it looks like after we take them apart and put them back together, we have a water molecule, but we also have some leftover parts in here. And if we go back to the chemical equation does not show that we have any leftover parts. The chemical equation shows that we simply have water as a product. And so it doesn't count for these leftover parts. So what I'm going to do here is I'm going to step back for a moment, and I'm going to do this. I'm going to put this hydrogen molecule and oxygen molecules back together. And now this time, instead of starting with one hydrogen molecule, I'm going to start with two hydrogen molecules. So it looks like this. Now what I'm going to do is I'm going to come back to my chemical equation, and to indicate that I'm starting with two hydrogen molecules, I'm going to put a number 2 in front of the hydrogen. So this is telling us that we're starting with two hydrogen molecules and one oxygen molecule. Now, typically in chemical equations, the 1s are implied. We don't write them. So even though we could put a 1 in front of here, it's implied that there's a 1 in front of there. Just like if we were doing algebra, if we saw x and we saw 2x, the number that would be in front of here, if we put one here, would be the number 1. So 1s are implied. Same thing when we write chemical formulas. The 1s are implied down below here. We don't write the 1s in. Okay, so now we come back and we want to look at what happens in the chemical reaction. We have our two hydrogen molecules and the one oxygen. they are going to wind up colliding together. Once they collide together, some bonds are going to break, and other bonds are going to reform. And so we'll form a water molecule here, and as we put these back together, we'll wind up forming another water molecule here. And at the end, how many spare parts do we have left over? None. But how many water molecules do we see? 2. So we come back then to our chemical equation, and if we want to show that we now produced 2 water molecules, how do you think we write that? 2 in front of H2O, exactly. And so what we have yielded here is what we call a balanced chemical equation. This here is a balanced chemical equation. And before we put the number 2 in there, we would have called this an unbalanced chemical equation. So this here is an unbalanced chemical equation. By putting the 2's in front of here, we would call this a balanced chemical equation. And a balanced chemical equation is one that conforms to the law of conservation of matter. And the law of conservation of matter says we can neither create matter nor destroy matter as a result of a chemical change. Now, back when we were looking at chemical change and physical change, we maybe didn't use the word chemical reaction, but a chemical reaction and a chemical change are the same thing. So again, a chemical reaction is the same thing as a chemical change. And we're running out of room here. There we go. Chemical reaction, chemical change represent the same thing. Now these numbers that we write in front of the balanced chemical equation, any idea what these are called? These here are called coefficients. And where have you heard of coefficients before? You've heard it in algebra and math. And what are coefficients in math? So if we saw something like 2x, what is the coefficient? 2. That's the number that goes up front, and this here would be a variable. Okay, so this here's the coefficient, this is the variable. And so the same thing is true in chemistry. Those numbers that we write out front are called coefficients. And in mathematics, what does it mean we do when we have a coefficient in front of a variable? We multiply, exactly. It stands for a multiplication. So if we had some equation which says 2xy, that means we have 2 times x and 2 times y, or 2 times x times y. That's in there. So it could be any one of these combinations. 2 times x, or 2 times x, 2 times y, or 2 times x times y. So it just means we're multiplying by 2. And they work the same thing here, same way in chemistry. What this means, if we wanted to count total number of hydrogen atoms, we'd have how many altogether?
4.
And we get that by taking 2 times 2. How many oxygen atoms would we have here? 2. How many hydrogen atoms do we have over here? 4. And how many oxygen atoms? 2. So we're just getting the 2 by taking 2 times 1, which is the subscript that we have over here. And of course, if we went back and looked at these atoms over here that we just had out, we do in fact have 4 hydrogen atoms and 2 oxygen atoms. So it stands for multiplication when we write out that chemical equation. So any questions on this particular reaction or demo? Okay, let's look at another one. This one here now, we're going to take some magnesium metal. And I need my safety glasses again. Here we go. We're going to start with some magnesium metal. And this time, I'm going to take this magnesium metal and grab the tongs. We'll start the flame. Actually, I wonder if I can do it with this. Get the bigger flame, that's better. And we'll turn the lights down once again. And we're going to look at this now in a little bit different context. And we'll go ahead and look at this under the dot cam. And looking at under the dot cam, we see that we have a strip of metallic magnesium. And what I'm going to do here is I'm going to turn the lights down. This will be something now that you do not want to look at directly, but rather look at it off to the side, or you can look at the dot cam when we do this. And you can see now that this is indeed reacting very brightly. And I need to be careful with the magnesium because this is really, really, really hot. And so if I let this drop down while it's still really hot, it could wind up burning a hole into the cable. So now if we look at this, once the reaction is complete, we should see upon this reaction being complete, what we're left with here now is a white powder. So we want to write out a chemical equation as to what happened here. We'll start with a word description of what we observed. And as far as the word description goes, let's start off with what this metal was. The metal again was magnesium metal. So magnesium metal reacts with, and what do you think it reacted with? Oxygen, exactly. Now we don't know that for sure, but typically if you see things burn, that means they're reacting with the oxygen in the air. So magnesium metal reacts with oxygen gas to yield. And what do you think we made?
Oxygenated magnesium.
Well, there's not a whole lot of options here. For magnesium with oxygen, it's going to have to make magnesium what?
Oxide.
Oxide. Magnesium oxide. Exactly. There's not a whole lot of options. If you have two elements together, they must react together. And so we make magnesium oxide, and the phase of this magnesium oxide was what?
Solid.
Solid. Right. So it's to make a magnesium oxide solid. So now we'd like to write out a chemical equation for this reaction. We'll start out with the magnesium metal. The formula for magnesium is Mg. The phase label would be S. And M is not a state. All our metals are which state? All the time?
Solid.
Solid, with one exception, that exception being
Mercury.
mercury. And how can we look at this periodic table and know that mercury is different than all the rest of them?
Well, because it's blue.
You can see that it's blue, and the ones that are blue here, these are liquid at room temperature. So if you look at this periodic table, the way that this is color-coded is, those that are in black at room temperature are in the solid phase. Those here that are in blue are in the liquid phase at room temperature, and those that are in red are in the gaseous phase at room temperature. So you'll see hydrogen over here, and then you'll see these noble gases, and then the nitrogen, oxygen, fluorine, and chlorine. These here are all red, and that's because they're gases at room temperature. So magnesium will react with oxygen. Formula for oxygen is O2. Phase label would be G. Now we are going to make magnesium oxide. Formula for magnesium oxide is going to be MgO. Well, now, how do we know what the formula is? Exactly, we need to look at their charges. So while it's real tempting to put MgO2 in here, because we see one magnesium here and two oxygens here, that's not the way it works. The way it works is we come back to the periodic table, we see where magnesium is located, Magnesium is in group 2A, which means its charge is 2 plus. Oxygen is in group 6A, which means it is 2 negative. So if we have a 2 positive and a 2 negative, what happens to the charges? They cancel out, and that means we have one of each. The formula for magnesium oxide is MgO. Now again, we can't leave the charges in there, because if you leave the charges in, that's something that is not a part of the chemical formula. Master in Chemistry will mark it wrong. If it comes to exam time, it'll get marked wrong. And then the phase label would be S, because it's a solid. Well, now we still have a problem, and the problem is on the left-hand side we see how many oxygen atoms? 2, and on the right-hand side we see 1. So now we need to balance the chemical equation. And the way we balance the chemical equation is by changing the coefficients. You cannot change the subscripts, because if you change the subscripts, you are changing the chemical formula. And the chemical formula of magnesium oxide is not MgO2. So to balance it, we change the coefficient, and the coefficient in this case would have to be a 2. And just like in algebra, where are the coefficients always written? At the front. We don't write x to y, even though it might mean the same thing. The convention in mathematics is that the coefficient always goes at the front of the formula. Okay, so the same thing is true in chemical equations. Coefficients are never placed in the middle. We would never write here. The coefficients always go out in the front. But now, because we put a 2 here in front of the MgO, how many magnesiums do we have here? 2. So over here we need to put 2 in front of the magnesium, and this then balances the chemical equation. So any questions that you have in balancing this? Okay, and again, remember the magnesium oxide comes from the fact that we have Mg with a 2 plus charge, O with a 2 negative charge, and that's then what leads to this formula. But if you were asked to write a balanced chemical equation for this reaction, this here is what we would write for the balanced chemical equation. Let's try another one. Let's write out this reaction. Nitrogen gas reacts with hydrogen gas to produce gaseous ammonia. Let's write out a balanced chemical equation for this reaction. So to write out a balanced chemical equation, we need to start with nitrogen gas, which is going to be N2 with phase label of G. And it's N2, not simply N, because nitrogen is one of the diatomic elements right here. It's one of your diatomic elements. We always write it paired up. It'll react with hydrogen, which is H2. Phase label is gas. And then it's going to produce ammonia, which has a formula of NH, not NH4, NH3. Now you say, wait a minute, how are we supposed to know that? These are our notes from Tuesday, and this is one of the formulas that is to memorize. Just like we memorize water is H2O, we don't call water dihydrogen monoxide. We call H2O water. Same thing when we see ammonia, we don't call it nitrogen trihydride, we call it ammonia. So there are some chemical formulas that have a common name. And it's not to be confused with the ammonium ion, which has a formula of NH4 with a plus charge. So again, this is to memorize. If you've forgotten that, circle this, and just remember, this is something that you need to memorize the formula of. Phase label here is going to be a gas. Now, once you see this, we need to now balance this chemical equation. And one of the things that I passed out here as you came into class today was this sheet. And if you look at this sheet here provides you some strategies for balancing chemical equations. Now, when we balance chemical equations, we use a method called balancing by inspection. And balancing by inspection is a fancy name for trial and error. You try something, if it works, great. If it doesn't work, you try something else. That's what balancing by inspection means. It means that we're looking at it, but we're really just trying something to see if it works, we try something else. So these are not rules. These here are what we call strategies. And by strategies, that means it's just simply something that we can try to do to help eliminate the number of errors. So when we look at a chemical equation, here are some of those strategies. First of all, we look at the chemical equation and we always wait to balance the simplest formula or element last. Next thing we do is we use the least common multiple between two numbers to try to balance something. Thirdly, when necessary, we use fractions to balance a chemical equation. And then we multiply it through with an integer that removes those fractions. And then there's something that we call even odd. And we'll describe these two in a bit. For this particular one, we'd probably use these two strategies right here. So I would look at this one, and I might look, now we could really pick either one of these as being the simplest. Let's say that nitrogen is the simplest simply because it comes first, and we see that there's just one nitrogen here. So we want to balance the nitrogen last because it appears to be the simplest. So we're then going to look at the hydrogen. If we look at the hydrogen, we see 2 on this side and 3 over here. And so if we see 2 on one side and 3 on the other, then a strategy that would probably work with this would be the least common multiple between two numbers. And so the least common multiple between 3 and 2 is 6. So how could we make 6 hydrogens over here? All right, we put a 3 here. And how could we make 6 hydrogens over here? Put a 2 in front of it over here. And so again, that's giving us a total of 6 hydrogens here and 6 hydrogens over here. We can then look at nitrogen. How many nitrogens are shown here? 2. And how many nitrogens are shown here? 2. And at this point, we would say we have a balanced chemical equation for the chemical reaction. Now, there's nothing that says that we would have had to leave nitrogen alone first. We could have looked at this one to begin with and said, well, hydrogen looks the simplest to me over here, so I'm going to start with nitrogen. You see 2 here and only 1 over here. You could then put a 2 in to balance the nitrogens. You'd see that this gives you 6 hydrogens. To make 6 over here, we could put a 3 in front of the H2. Either way, in the end, we wind up with the same balanced chemical equation. Now, even after doing this a few times, sometimes students will struggle with balancing chemical equations. So here's another strategy you can use. You can make a table. And in your table, what you're going to do is you're going to list the elements. And so the elements here are nitrogen and hydrogen. And we're going to look at the reactant side, and we'll look at the product side. Which is reminding me of a couple new terms that we haven't talked about yet. They are the terms reactant and product. So if we come back to our original one that we looked at, that is with the hydrogen and oxygen, everything that appears on the left-hand side is what we call a reactant. And everything that appears on the right-hand side are what we refer to as a product. And actually, if we have more than one of a reactant, like in this case we have 2 reactants, we just pluralize it. We refer to them as reactants. And if we have only a single product like we do right here, we'd simply say that there is one product. But every chemical equation must have one or more reactant, and it must have one or more product. So if we come back to our chemical equation here, one of the things you can do, let's say if we started with it unbalanced, we could look at it something like this, is we could make a tally. And so before we begin, And by tallying, it's just like putting in, if you ever counted like this, just simply putting in tallies to count how many there are of a particular element. So before balancing it, we can look on the reactant side and count how many nitrogen atoms are there. There are 2. How many hydrogen atoms are there?
2.
If we look on the product side, how many nitrogens are there? 1. And how many hydrogens are there?
3.
There's 3. So the whole idea when we balance chemical equations is to make the tallies for each element the same on each side. So if we did start with a nitrogen, we saw 2 here and 1 here, and we wound up putting a 2 in front of the NH3. We now count the number of nitrogens and how many are there? There's 2 here, so we could then tally that as 2. And how many hydrogens are there? There's 6, so we could put in a total of 6 hydrogens. Well, now we see that the nitrogens are balanced, but the hydrogens are not. So to make the hydrogens balanced, we need to put a 3 in front of there. Once we put a 3 in front of the H2, we then have 6 hydrogens over here. And so then by actually tallying them up, we can see now that the number of nitrogens are the same and the number of hydrogens are the same. So for those that need to be a little more visual, this is a way that you can count them out rather than just doing it all up here in your head. So again, those are some strategies that may work for you. So any questions on the 3 examples we've seen thus far? Okay, let's try these out. Let's try. Now I'm not going to show the phase labels on these. I'm going to show vanadium reacting with oxygen to produce vanadium 5 oxide. We'll show aluminum reacting with oxygen to produce aluminum oxide. And we'll show potassium chlorate decomposing to yield potassium chloride plus oxygen. So now take these 3 equations and balance them. So again, take these 3 equations and balance them. And remember, when we balance them, the only thing we can change is the coefficient. We cannot change subscripts. So go ahead and act. Correct answer is 5. And so if we look at it 2, 3, and 5, let's go back and see how we'd balance this. What is the simplest formula in this particular equation? The V, which means we should balance the V last. So we look to the oxygen. How many oxygens here on the left? 2. How many on the right? 5. So that means we should find the least common multiple. Least common multiple between 5 and 2 is 10. To make 10 oxygens, we'd put 5 here and 2 over here. This makes 10, this makes 10. What else do we need to change? The V, which would need a 4, because 2 times 2 over here is 4. And that's how you go about doing it. Now when it comes to multiple choice, like if you'd see this on exam, it's kind of hard to ask this in a complete multiple choice. But we could say, what is the smallest possible coefficient here in front of the O2? And that's important or key to the wording on this. Let's see, where is the wording? Right back here. The smallest whole number coefficient, the coefficient of O2 is, and of course that then would be a 5. Next up, let's try this one. You should have already gone through and balanced these. So go ahead and enter them in. We have the smallest whole number coefficient on the O2. once we get up to 30 on here. We'll count down. Here we go. And that correct answer, the sum of the coefficients, is 9. So now if we look at how we wind up with 9, we come back to this one here and we then ask ourselves, which is the simplest formula? What is the simplest formula in here? Al. So we're going to balance Al last. So we go to the oxygen. How many on the left?
3.
On the left?
2.
2. On the right there would be 3. So we use the least common multiple. Least common multiple of 3 and 2 is 6. So to make 6 oxygens on this side we need to put a 3 here. And on this side we need to put a 2 in here. What else then needs to change? Aluminum. And how many aluminums do we have? 4, which means we need to put 4 over here. The sum of the coefficients, 4 plus 3 plus 2 is 9. And 4 plus 3 plus 2 then makes 9, and that would be the answer then for this one here. So again, these are how you're going to see these worded as multiple choice questions come the exam. We get to the next one here. When balanced with the smallest whole number coefficients, what is the coefficient on KCl? So in other words, we want to know what is the number that goes in front of the KCl right here. And we'll wait till we get up to 30.
Bless you.
There we go. And that coefficient is a 2. Very good. And so balancing this one here, coefficients in front of the potassium chlorate would be 2. This would be 2, and the last one would be 3. And this then is the balanced chemical equation for this reaction. So any questions on these? Okay, now this last one, if we wanted, we could have balanced this last one like this. And so I'm just going to write it out. This would have also been balanced if we had put 4, 4, and 6. Because if we counted potassiums, how many potassiums are there on each side? There's 4. How many chlorines are there on each side?
4.
And how many oxygens are there on each side?
12.
There's 12. Okay, so this is also balanced. But what do we notice about these coefficients?
And now we're the smallest.
They are not the smallest. And each of these here are divisible by 2. So when possible, or if you encounter a situation like this where they're all divisible by the same number, we would then basically, actually what we do is we take the entire equation here and would multiply it by a factor of 1/2, which means we're basically going to divide all of these coefficients by 2. We divide them by 2, we wind up with the one that we see right here. So even though we might be able to write it like this, and this is particularly true and what's frustrating for some students I'm answering chemistry, they say, I know I balanced this equation, I know that balanced this equation. But if you know you balanced it and your coefficients look big, chances are what that means you're still doing it correctly is you've forgotten to reduce them down. So always here when we write out a balanced chemical equation, we want to reduce them down to the smallest whole number coefficients that are possible. Okay, we're going to look at another reaction here. In this reaction, we are going to take some hydrogen peroxide and we are going to add to it another chemical. There we go. I'll put the hydrogen peroxide in here. transfer it in. And now you should not know the chemical formula of hydrogen peroxide unless you've studied that type of thing, and this is not one I'd expect you to know. But if you did know it, anybody know what the formula is for hydrogen peroxide? H2O2. O2, yes. And the hydrogen peroxide I have here is dissolved in water, which means we put a phase label of AQ, which again stands for aqueous, or dissolved in water. Now what we're going to do with this is we're going to cause this hydrogen peroxide to decompose. We're going to cause it to decompose by adding in catalyst. And the catalyst we're using here is manganese dioxide, or manganese 4 oxide, I guess, because it's an organic name. So what I'm going to do here, before I actually do this one, I need you to close your eyes and make a wish. Okay, I can open them up. And I'm going to put it in here. I'm just going to rub the bottle here. And with any luck, my genie's kind of slow to come out of the bottle here. Does not want to get very active. Maybe we need to give the genie a little help. We'll add a little more of this stuff. There we go. All right, so now, I call this my genie in the bottle demo. Pretty cool, huh? So, now if we want to write out a chemical equation for this, the reaction would be the hydrogen peroxide decomposes to yield, and I'm going to write out a word description for this. Hydrogen peroxide decomposes in the presence of a manganese 4 oxide catalyst to produce, and we're producing water and oxygen gas. Manganese 4. Well, now there's a new word in here, and that is the word
Decompose.
well, I guess maybe decompose is too. Decompose means that we take something apart, and then we have the word catalyst. And a catalyst, anybody know what a catalyst is?
It causes the reaction to happen faster.
What does it do to a reaction?
It speeds it up.
Speeds it up. So we say the catalyst speeds up a chemical reaction and it's more than just that, and it is without being consumed. So what that means is that if I added 1 gram of manganese 4 oxide, if I added in 1 gram of manganese 4 oxide, in the end here I should have 1 gram of manganese 4 oxide. Okay, so it's something, whatever we start with, we should also end with. Well, in a chemical equation, we write a catalyst above the arrow. And so we need to know the formula for manganese 4 oxide. So if we want to write the formula, manganese 4 means we have Mn with a charge of 4 plus or minus positive. Oxide is O with a charge of 2 negative. So we have Mn with a charge of 4 plus, O with a charge of 2 negative. That means its formula is Mn O2. Because we need 2 of the oxides to balance the charge of the 1 manganese. And so, again, in a chemical equation, the catalyst is written above the arrow. So again, the catalyst is written above the arrow. And then our products in this case are water and oxygen. So the formula for water is H2O. And of course, what is the phase label of water?
AQ.
It's not AQ.
L.
It's L. And why is it not AQ?
Can't dissolve water in water.
You can't dissolve water in water, exactly. It's a common mistake though. So water is a liquid, and then oxygen would be O2. Phase label here would be
G.
G. So now that we have this, let's go ahead and balance this chemical equation. Let's balance this chemical equation. And so I'm going to pause this here. And once you get this one, go on and balance this next equation. Next equation I'm going to have you balance is N2H4 breaks down to yield NH3 plus N2. So we'll check this out. Correct answer here is choice E. Choice E. Why is choice D impossible?
Because can't have a zero.
Can't have a zero. If we don't put a coefficient in front of there, the coefficient that's always implied is a coefficient of 1. So we could right away rule out choices A and D. So now to do this one, if we want to look at it, there's actually a couple different ways we go about balancing this one. First of all, we start with the hydrogen peroxide making the H2O and the O2. We have the MnO2 catalyst. And this is where we look at those strategies. Now I know I didn't direct you to these strategies, but sometimes the strategy number 3 or number 4 are ones that would help. And let me show you how these are applied. First of all, if we look at this equation, which one is the simplest formula? Probably the O2. If we see an element by itself, we leave it to last. So that means we then balance the hydrogens. How many hydrogens on the left? 2. How many on the right? 2. Which means they're already balanced. So then we look at the oxygens. How many oxygens here? 2. How many on the right hand side? There's 3. Now, one of the ways we can balance it, since the hydrogens are already balanced, we don't want to mess around with the coefficient here. That means we want to put some coefficient here in front of the O2 in order to balance this chemical equation. So we need to look at oxygens. And again, right here, how many do we have? There's 2. How many hydrogens, or excuse me, oxygens are there here? 1. And how many oxygens are there here? 2. Now we know that it's going to be some number times 2 plus 1 is going to equal 2. Now in algebra, if we want to say some number times 2, how could we write that algebraically?
X times 2.
X times 2, which we ordinarily would write as 2x. So we'd say 2x plus 1 is equal to 2. Well then, to solve for x, we're going to add 1 to each side. So if we add 1 to each side, no, we're not going to add 1, are we? We are going to subtract 1. If we subtract 1 from each side, we get 1 is equal to 2x which means that X is going to be equal to how much? 1/2. And so we put a 1/2 here in front of the O2, and that then will balance the chemical equation. Because, of course, 1/2 times 2 is 1, plus 1 here then makes 2, and that balances the 2 that are on the left-hand side. Of course now, according to this here, we cannot leave fractions in there, so we're going to multiply it through by some integer that will remove those fractions. And so that means we would take this entire equation and multiply it by an integer value of 2. If we multiply it through all by 2, then 2 times 1 is 2. 2 times 1 is 2. And 2 times 1/2 is 1. And this leads to this particular balanced chemical equation. Now another way we could think about it is to look at the last rule here, which is what we call this even-odd. And this describes how this works. It says if one side of an equation can only have an even number of atoms of a given element, and the other side has an odd number of atoms of the same element, place an even coefficient in front of the formulas to make each side have an even number of atoms of that element. So in practice, if we came back to this one and want to look at it from this perspective, we already said we were going to leave oxygen to last. So we then look at hydrogens. We see that it's balanced. We go back to the oxygens. And how many oxygens are there on the left-hand side? And how many on the right-hand side? There's 3, which of course is an odd number. And we have an even number on the left-hand side. So how can we make an even number on the right-hand side? And we'd have to put what type of coefficient here in front of the H2O? An even number. And the smallest even number we can start with is a 2. If a 2 doesn't work, we would try a 4. And if a 4 doesn't work, we'd try a 6, and so on. So we tried different even coefficients. But we didn't try the 2 yet, so we try out the 2. And by trying out the 2, that's going to give us 2 oxygens here, plus 2 more here, giving us 4. And so if we want to make 4 oxygens on the left-hand side, we'd put 2 in front of the H2O2. That then gives us 4 oxygens here to balance the 4 on the other side. We then have 4 hydrogens to balance the 4 hydrogens, and this winds up being a balanced chemical equation. So this here is how we deal with balancing chemical equations. Any questions on these? All right, here's where we're going to go on Tuesday in here. On Tuesday, we are going to look at completing and balancing chemical equations. And in completing and balancing chemical equations, we are going to look at 2 different types that we will be responsible for. First type is going to be what we call double displacement reactions. Actually, we're probably going to look at combustion reactions first. And then the second type we're going to look at is double displacement. And double displacement is also often referred to as double replacement. And we're just going to give a very quick preview to combustion reactions. Now, what do you think of if we think of combustion?
Fire.
Fire, exactly. This means we're burning something. And if we burn something, that means which element always needs to be present? Oxygen, exactly. So this means to react in the presence of oxygen. Of course, an oxygen has a formula of O2. And what we're going to do is we are going to assume complete combustion. Now, when we do this, here's what we're going to say. We're going to say if a reactant contains these elements, let's say if it contains carbon or hydrogen or sulfur, here's what's going to happen. If a reactant contains carbon, it is going to get converted to CO2. If it contains hydrogen, we say it's going to be converted to H2O. And if it contains sulfur, that means it's going to get converted to sulfur dioxide. It's going to take us to the last demo here today. It's going to be a very simple one. It's this one right here. The stuff that goes into here, out of this hose, is called natural gas. And the primary component of natural gas is methane, which is a formula of CH4. So if we wanted to write out a chemical reaction for this, we'd write it as CH4 is going to react with oxygen. To react with oxygen, this now contains carbon, which means it's going to get converted into CO2 and H2O. And so on Tuesday, we will start with this. You should be prepared to write out a balanced chemical equation for this reaction. That's it for today.